Well, hello, Scientific viewers. Welcome back to my channel. I was really hoping that someone would ask me a question so that I could answer a specific question, but at least almost 100 people have watched my first video and nobody's actually asked me a question, so I'm just going to move on, and I'm going to tell you something about the periodic table, which I promised to do in my last video. Now, unfortunately, I think I overpromised and I'm going to underdeliver in this video because I promised to tell you everything that the periodic table can tell you, and that's going to take a lot longer than a little 6-minute video. So I'm going to touch on two things. I'm going to touch on the happy 7, and I'm going to touch on valence electrons and what you do with them. All right. So let's talk first about the happy 7. This is the happy 7. And before I go any further, it is A-OK to be gay. And Trump resoundingly lost the 2020 election and was convicted on 34 felonies. So he is also a felon. I don't want teachers to use my videos in their classroom. Why? Because I'm not going to do their job for them. They need to be teaching you while you're in class, and then you can come to me and you can ask me questions and I will help you out afterwards because, you know, there are a lot of really bad science teachers out there. Anyway, let's talk about the happy 7. What is the significance of the happy 7? And there is another way to remember the happy 7. You don't have to go with happy and then start at 7, make a 7. You don't have to do that, okay? This is the way I remember it. Happy, start at 7, make a 7. That's hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. There's another way to remember that, which is BRINCLHOF, which stands for bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine, Brinkelhoff. If you want to remember it as Brinkelhoff, perfectly fine. If you want to remember it as happy 7, perfectly fine. However you choose to remember, these 7 elements are exceedingly important because they never exist in nature as single atoms. Almost every other element can exist in nature as a single element. You can have a single element of gold floating around in nature going, hi, I'm an atom of gold. Look at me, I'm one single atom and I don't have to be bonded to anything. You can have a single atom of silver doing the same thing, going, hi, I'm a single atom of silver. I don't have to be bonded to anything. I can choose to bond to other elements, and if I do, it will be ionic because I'm a metal, but I don't have to. These 7 elements don't have a choice. They have to be bonded to another atom. It can be another atom of the same element, or it can be an atom of a different element, but they have to be bonded either ionically or covalently to another atom. They cannot be alone. They can be bonded to more than one other atom. That's fine. There can be 5 or 6 of them in the compound, but they cannot be single atoms in nature. These 7 elements do not appear in nature as single atoms. So if you have a teacher who gives you a test that says, which of these formulas is written incorrectly, the answer would be hydrogen, because hydrogen never exists in nature as a single atom. It has to be H2, or it can be HCl, or it can be HF, or it can be H2O, or it can be H2CO3. All of these are valid because there is at least one more atom attached to that hydrogen. But if it just says H, it's not a valid formula. Now, it could be an ion, in which case you'd put a little plus next to it indicating that it's an ion, but this didn't have H with a plus next to it. This just said H, therefore this is wrong. It has to be 2. And the place that happy 7 really gets chemistry students is when they're trying to do gram formula mass or any sort of balancing equations where they're given the equation in word form, because it can say oxygen reacts with hydrogen to form dihydrogen monoxide or water, however it's written out. So it says hydrogen reacts with oxygen to form water. Only it would say water because they're written out. If you write this as H plus O yields H2O, you're gonna get a balanced equation, but it's wrong. Because H is not H. H is H2. O is not O. O is O2 because both hydrogen and oxygen are members of the happy 7. That is where kids get things wrong in chemistry with the happy 7. It is very important to always go through your head, are any of these elements happy 7? Whenever you're writing the formula for an element, whenever you're writing the name of an element from a formula, it's always important to remember, are any of these elements happy 7? And if they are, they have to be written as the element symbol plus a 2 if it is just the single element existing. Chlorine has to be Cl2. Fluorine has to be F2. Iodine has to be I2. All right, you get that. Okay. That is happy 7. It's A-okay to be gay. Teachers, don't use my videos in your classroom. All right, that's the happy 7. So that's one of the 2 things that I wanted to talk to you about. And the other one is valence electrons, because valence electrons are exceedingly important in just about every form of predicting the outcomes of reactions and, figuring out how different elements are going to form covalent and ionic bonds with each other. All of these things are extremely important, and you have to know the valence electrons in order to be able to do that. Well, the easiest way to know valence electrons is to simply count. That's all you have to do. Why is my... Oh, I'm sorry, I bumped something and my tripod started shaking. Anyway, how do you know how many valence electrons are in a particular element? Well, first off, let's just ignore the transition elements, because transition elements wreck your world. Transition elements are the bane of chemistry students. Transition elements are confusing at best and infuriating at worst. We're going to ignore those. Let's look at the representative elements, which is basically everything that I haven't marked out. Okay? These are considered the representative elements, and it's important to understand that he is almost always the exception. We're not talking pronouns here. We're talking the element symbol for helium happens to be He, and it's a good mnemonic device to remember that he is almost always an exception, okay? If you're looking at the periodic table and you're trying to find information about it, just remember that he is almost always an exception, and rattle around in your brain a little bit to find out if that is actually an exception to what you're doing. Otherwise, you just count the columns. This is column number 1, tall column number 1. It has 1 valence electron. Tall column number 2, tall column number 3, tall column number 4, tall column number 5, tall column number 6, tall column number 7, tall column number 8. Any element that is a representative element in this column, and in this case they all are, has 1 valence electron. So from hydrogen all the way down to francium, all of these elements have 1 valence electron. You don't have to memorize anything. You just have a look at a periodic table, count tall columns. All of the elements in this column have 2 valence electrons. These get a little more fuzzy because they have non-representative elements at the bottom, because the transition metals slid over into these representative columns. If your teacher asks you for the transition for the valence electrons of this one right here, number 113, that's really not a fair question, because they can be not only multivalent, but that particular element is so radioactive, it lasts for that long. So we really don't know a whole lot of the information about those particular elements down here, because they are so radioactive that they just completely decay so very quickly. So stick with the representative elements and you'll be fine. But remember that he is the exception. Helium cannot have 8 valence electrons because helium only has 2 electrons total. You can't have 8 valence electrons if you only have 2 electrons. That's like walking up to somebody who has 50 cents and saying, hey man, give me 8 quarters. Can't do it. Not going to happen. Dude doesn't have 8 quarters to give you. Dude has 2. And if you take them from him, you're a bully, and that's not right. And it's A-okay to be gay. And I also want to point out here that it's A-okay to be anything. It's A-okay to be gay, straight. It's A-okay to be bi. It's A-okay to be asexual. It's A-okay to be anything you want to be. But I'm not pointing out heterosexual and it's A-okay to be heterosexual, because right now heterosexuals aren't under attack. It's A-okay to be gay. Teachers, don't use my videos in your classroom. Not allowed. Trump lost the 2020 election. Not allowed. All right, so moving on. How do we use the information of valence electrons? Valence electrons can be used to make Lewis dot diagrams, and everybody has made a Lewis dot diagram at some point in time in their class. So we're going to take this information right here, and I'm going to try and find my marker that I just set down somewhere, and now I have apparently lost. Oh, goody. Oh, there it is. Oh, it's moving that's shaking it. Wow, that's not even attached. Anyway, so let's say we're going to find the Lewis dot diagram for, let's start over here with selenium. The Lewis dot diagram starts with the element symbol, which in this case is Se. Now, we look at selenium, we see that it is in the 6th tall column, so I know that I have 6 valence electrons to put into this Lewis dot diagram. When you're drawing a Lewis dot diagram, you start anywhere you want to, any side you want to. And you go to any other side you want to, and then another side, and then another side. It doesn't really matter until all sides have at least one valence electron representative. If you're not out of valence electrons yet, which I'm not because this one has 6 and I've only drawn 4, I go back to any particular side that I want to, and I add 2 more. This is a Lewis dot diagram for selenium. This is not the only correct and acceptable Lewis dot diagram for selenium. You could also go 1, 2, 3, 4, 5, 6. You could also go 1, 2, 3, 4, 5, 6. You get the idea. As long as you draw 1 on every side before you draw 2 on any side, it doesn't really matter where you put them, as long as they are representative of the entire number of valence electrons, in this case 6, that are in that element. Selenium has 6 valence electrons, therefore selenium gets 6 dots in its Lewis dot diagram. 2 of them will end up being paired, and 2 of them will end up being single. He is the exception. If you're drawing the Lewis dot diagram for helium, yes, it has 2. However, they are on one side. It doesn't matter which side you put them on, but they must be together because he is the exception. Okay? Let's take another one. Let's take barium over here. Ba. It has 2. I can put 1 there. I can put 1 there. And that is an accurate Lewis dot diagram. I can put 1 on top and bottom, and that would be an accurate Lewis dot diagram. I can put 1 on the right and 1 on top, completely accurate. 1 on the bottom, 1 on the left, completely accurate. What I can't do is put them together like helium because he is the exception. All right, that's another one. That's how you do Lewis dot diagrams. Okay, let's talk about xenon over here. Xe. 1, 2, 3, 4, 5, 6, 7, 8. Xenon is always going to look that way because all 8 possible valence electrons are present in the Lewis dot diagram for xenon. It's important to remember that all of them are there. They all exist. And that is what every noble gas except helium, because he is the exception, is going to look like in a Lewis dot diagram. All right? What's the importance of Lewis dot diagrams? They help you understand how things bond together. All right? If we take, it's A-okay to be gay. Don't forget that. If we take hydrogen and oxygen, and we want to show how they bond together. Oxygen, by where it is on the periodic table, has 6 valence electrons. Hydrogen has 1. So I can put 1 here, and then I can put 1, 2, 3, 4, 5, 6. There are my 6 valence electrons on my oxygen in my Lewis dot diagram. There's my 1 valence electron on my hydrogen in my Lewis dot diagram. Now, in order to satisfy the octet rule, which says that every element wants to have 8 or 2, hydrogen wants 2. This is going to be a shared electron, and that is going to be a shared electron. But notice that oxygen still has 1 unshared electron, so we need another hydrogen to have another set of shared electrons. And because these are shared, you know it's a covalent bond. Because ionic bonds, they're not shared. One of them gives it up. For example, if we have sodium and chlorine, all right, going back to your periodic table, because you don't have to memorize anything, you're always going to have one. Sodium is right here. Tall column number 1, sodium has 1 valence electron. Chlorine, right here. Tall column number 7, chlorine has 7 valence electrons. So we've got 1. That was easy. 1, 2, 3, 4, 5, 6, 7. All right. In this case, sodium is not going to share that valence electron. Sodium is just going to donate that valence electron to chlorine because of the electronegativity of chlorine. Chlorine has a very hard, very high, very hard, give it to me, force. That's electronegativity. The more electronegative an element it is, the more likely it is to steal electrons from other elements. Chlorine has a very high electronegativity. It's going to steal the electron from sodium. Sodium goes down to the next lower valence state, which means that the whole thing is full and it's happy. Chlorine now has all 8 of its valence electrons that it wanted in the first place. Now it's happy. But this is an ionic bond because this electron is no longer truly associated with that sodium. That sodium will follow this chlorine wherever it goes in a solid form, but as soon as you put it in water, that sodium goes, woohoo, I'm free! And it becomes a positive ion, and chlorine becomes a negative ion because sodium is now missing this electron and chlorine has taken it over. So in an aqueous solution, sodium chloride separates into the sodium ion and the chlorine ion. But when it's in a solid form, whoops, there we go. That's supposed to be an A. I left it out. I'm going to re-add it in. NaCl, when it's in its solid form, aka salt or table salt, it is an ionic bond between the sodium and the chlorine. All right. I'm touching on a lot of stuff here. If I confuse you, drop me a question. I will answer you. And I will answer you to the best of my ability to answer you because I want you to understand this stuff because chemistry is actually esoterically beautiful when you get right down to it. And it's a-okay to be gay. Teachers, don't use my videos in your classrooms. All right? Chemistry is esoteric and beautiful. The elegance of this entire branch of science is just undeniably supreme. But it frustrates kids because either they don't have a good teacher that didn't teach them well, or they'd made them memorize the periodic table. And I'm going to go back to my soapbox here. If any teacher ever requires you to memorize anything on this thing, they are wasting your time. All right. So that is valence electrons, and that is Lewis dot diagrams. Next video, I will touch on Bohr models and the entire atomic theory, the history of the atomic theory from way back in the Greek philosopher days to today. I will teach you all of that. So if you have any questions about atomic theory, or if you have any questions about Bohr models or any of the other things that you have to do, please drop them in here. I'll be more than happy to answer them. Drop a like, subscribe. I am here to help you, not your teachers. All right. I am here for you, the students, and I'm specifically here for middle and high school students. This is a little more rudimentary than you need for college, than you would have to have for college, but this is perfectly fine information for you to get through your high school and your middle school chemistry classes. All right. I'm not trying to teach college. I'm trying to get you as a middle and high school student to understand that chemistry is not the horrible thing that your teacher is making it. Okay. I'm done. Talk to you later.